Hello class, welcome back. So what we're going to do today is continue looking at addition reactions. And the next one that we want to look at is a reaction called halogenation. Halogenation is when you treat a, let's say, it is when you take a alkene and you treat it with a halogen. And that halogen, okay, right there, can be, let's see, chlorine and bromine. You do not use fluorine or iodine. Those are no. And the reason why we don't use fluorine is because it's too reactive / explosive. It's not going to get us a clean product. It's just boom, it just happens too fast. So we can't control it. Iodine is just too slow and gives poor yields. So halogenation only uses chlorine and bromine. And what happens is when it does this reaction, what we're going to get is an anti-addition. That's very, very important. That's a key feature of this reaction. You can see that you get no product that is syn addition. This is syn addition. These two are anti-addition. You do not get any of that. You can already guess how we're going to figure that out. Well, the mechanism is going to teach us why we observe this. This is an observation. We don't get that. Why? The mechanism helps us figure that out. Okay, so let's start looking at a mechanism to figure this out. So the first thing that we need to look at is the fact that we have our cells, a alkene. That's what I'm trying to represent here. And so that is what? Electron rich, right? And let's say we're going to treat that with bromine. That looks like this. And bromine also looks electron rich because of all these lone pairs, right? But guess what? Bromine and chlorine are rather large, so they're very polarizable. So at a given moment of time, this molecule can polarize and put electrons on one side and less electrons on another. So the bromine atom could look kind of like this. We'll represent it with a partial negative and a partial positive. So that's saying the electrons have shifted to the right. More electrons over here, less electrons there. And so when we look at bromine in this way, we can see, hey, this right there is electrophilic because it's electron poor. And so what can happen now is we have identified our electron-rich species, which is the alkene, and here is our electron-poor species, or the electrophile. And so we can have the alkene right here come in and attack that bromine. But we've learned from general chemistry that halogens can only form one bond. And so we would think that this goes like this. Okay? So what would that give us after this first step right here? We would draw this here. Let's say we added the bromine on this carbon right here. And then that would have left what? A positive charge on that carbon. And then we would have our bromide, this one right here, as an anion. Okay? So what is the hybridization state of this cation right here? Well, we know that is a what? A sp2. So it has a empty p orbital. And so we have this empty p orbital and it has a phase. Now look at this here. This bromide here now has a 50-50 chance. It can attack from the top or the bottom. Now let's take a look. If it attacks from the top, like so, what would our product be? We would have something that looks like this. We would have that. So this bromine right here is this guy, and then this one going down would be our dash. Okay? Perfect. That's an anti. But you have an equal probability that it can come in from the bottom. And if it came in from the bottom, then you would have something that looks like this. That is syn addition. And I just told you a few moments ago that syn addition does not occur. But the mechanism says, hey, it's a 50-50 chance. You should get half of it in a syn addition and then the other half in anti-addition. But we only see anti. So what does that tell us? Our mechanism that's proposed here is not correct. So we have to go back to the drawing board and be like, okay, why does this not work? So let's erase this incorrect mechanism and show you the correct mechanism. So just remember the way that I'm drawing these two structures. They're both the same, okay? Just drawing a little differently. This right here is in the plane, so representing my hand, right? But this representation of this molecule looks like this. I've rotated it 90 degrees. That's what I'm trying to portray. So maybe if I draw it a little bit more like, if I can try to get it to tip out more out of the plane here. Let's see, what's the best way? Maybe if I make those a little bit wider. Maybe you can see it now coming out at that I've taken this molecule here and just tipped it 90 degrees. And we have the pi bond right there. That's the representation that I want to look at. And the reason why I want to look at it that way is because when this alkene reacts with the halogen, and in our case we'll do bromine, the bromine molecule can approach from the top face of the molecule. So if we go back to my hands, I know I use my hands a lot, but if my hand is the molecule, the bromine can come from the top, or it can come in from underneath, like this. So there's a 50-50 chance of which side it approaches, because these are sp2 hybridized carbons. So this molecule is relatively flat, especially at these carbons right here. So it can approach from the top or the bottom face of this molecule. And each has the same probability, 50-50 chance. So if we look at it that way, our bromine here, I'm going to represent it like this, okay? And we've learned that we can have that polarized bond. So now we have our electrophile here. What can happen now is the previous mechanism was incorrect because it formed a carbocation, which then allowed the bromide to attack in from the top or the bottom, which would then give us a mixture of syn or anti-products. But we only get anti-products. And what we've learned is that when this pi bond or these pi electrons come in and attack the bromine, what happens is that the bromine has these lone pairs here that they use right away, like that. And then we have a third mechanism here, or a third arrow, that breaks that bromine-bromine bond. And so what that does for us is now what we have is what's called a bromonium ion. And how do I want to draw this right? So we got to go like this. So we have lone pairs, boom, down like that. So now that bromine right there is going to have a positive charge, and then the bromide that left has that. All right? So remember how we taught you in Gen Chem, halogens only have one bond? That's mostly true. We have now what's called a bromonium ion, which the way it's drawn shows it has two bonds, but these bonds aren't like complete, full-blown bonds. They're very, very, very weak. But we have this bromonium ion. So this bromonium ion can form from the top face or from underneath. Equal probability. Okay? And then the next step would be, hey, this bromine carbon bond is very, very weak. And so what we're going to have happen is that the bromide cannot attack from the top face. It cannot come in and attack the carbon like this. Why can't it come in from the top face? Because the bromine is already there. It's taking up that space. It can't attack from that angle. It has to attack from underneath. That's the only option. So it comes in from underneath and attacks. And if it attacks that carbon, then this bromine carbon bond has to break. Going back to the bromine right there. And what does it give us at the end of the day? We're going to have what? We have a bromine there because you see how this bond is already pointing up? Did I draw any arrows showing that bond breaking? No, so it just stays up. But then this guy came in from underneath. And so that guy is down. And so we can take this molecule and represent it like this. So this bromine would be that guy, and then that one would be that guy. So we have anti-addition. Okay? Let's see, anything else that we need to say with that one? If you decided to use chlorine, you would have a chlorine here, just like this, and we would call it the chlorinium ion. And you can see that this resembles the three-membered structure when we were looking at mercury, when we were looking at the oxymercuration, demercuration reaction. It formed that three-membered ring with the mercury. So the same concept. All right. Now, when we take a look at this again, could this bromine right here, could it have attacked this carbon instead? Yeah, of course it could. What if it came and attacked that one? Then this bond would have had to have broken, and we would have had something that looks like this. And so we had the bromine come in from the bottom. This bond was never touched, so we have our bromine there. Got to put those little gaps in there. Like that. Hey, do you see the difference between these two? Okay. So equal opportunities there. Those because the molecule, why is there no difference between these two carbons? Because there's symmetry. When you look right down the molecule there, there's nothing that says, hey, this side is better than this side. And typically when we want to pick sides, it has to do with electronic reasons or sterics. And the electronics are the same and the sterics are the same. So we have equal probability. But we will see some reactions where you're not going to have a symmetrical alkene or a symmetrical bromonium ion. So you can see the alkene also is symmetrical. And when we have things that are not symmetrical, then we're going to have some regioselectivity things that we need to look at. Now that regioselectivity that I was talking about doesn't necessarily apply to halogenation, because what are you doing? You're adding two of the same elements to one side. Remember with the other reactions when we were using HX, we were using the Markovnikov rule to say, hey, where does the hydrogen go? Where does the halogen go? But in halogenation here, we have two of the same elements. So we just know one halogen is going to go on one carbon and the halogen is going to go on the other carbon in a anti-addition. But if you change it up a little bit, if you instead use a halogen, okay, so chlorine or bromine, and you add water, things change, the reaction changes a bit. Okay? And changes also, the name of the reaction also changes. Okay? And that's called a halohydrin. So that's a halohydrin reaction. Halohydrin. And there's no E. Make sure I have it spelled right. The halohydrin is when you take a alkene, treat it with a halogen plus some water. And what you're going to get is a product that looks like this. Or okay. Do you see how that they are anti? You're not going to get syn addition. You don't get that product. It's only anti-addition. And it has to do with the mechanism because we are going to be forming a bromonium or a chloronium ion intermediate, that three-membered species. So the mechanism goes just like before. All right. So I'm going to skip the first mechanism step because we've already seen it. So let's use bromine again. So what we're going to get, okay, now remember the bromine can approach from the top face of the alkene or the bottom face. And I'm just going to say it approached from the top face. So that line's not the best. Okay, like that. Okay. So there's our bromonium, right? And we still have the bromide left over from that first step there. But in comparison to the water's the solvent in this case. So when you compare these two nucleophiles here, which one's more abundant? The water. Just so much water. So the water is going to come in and attack one of these carbons. And because this molecule is symmetrical, and we have an alkene that's symmetrical, the water doesn't, there's no preference for which carbon to attack because there's symmetry. So it attacks there, then this bond breaks to give us, and I'm going to drop down here. We will have our bromine right there, and then our water came in right here. Like so. Now we see that we have a positively charged species, and so we just need to do a proton transfer step where water is very abundant, and so we will say, hey, let's come in and grab that guy like so and give us our product. So we can draw it just like this here, and OH. Okay, just like that. Now could water have attacked on this carbon? Yes. Yes, it could have. Right? Oftentimes, instead of, hey, showing that the water can attack this carbon as well, you can just go plus an enantiomer. And so plus the enantiomer tells us, hey, there's the other enantiomer, which means the water would have had to attack that carbon instead. Okay? So now that you understand, or we have discussed the principles here of anti-addition, now let's start looking at an alkene that isn't symmetrical. So that poses some regiochemistry concepts that we need to be aware of. So here's a halohydrin reaction where we can see our alkene is not symmetrical. And in our product, we noticed that the water, which then gets converted into an alcohol, where did it attack? It attacked the more substituted carbon, and the halogen attached to the less substituted carbon. Why? What's going on here? Well, in order to do this, I want to take this molecule right here. You see that it's in the plane. Okay, and if I represent it like this with my hand, what I'm going to now do, now do you see how my thumb right here is going to represent this methyl group? I'm just going to rotate it 90 degrees. Okay, and so now my thumb is coming out towards me. So I'm going to represent it like this. Okay? So when we do the reaction here, let's move that out of the way a little bit, more like this, okay? And I made that bond really large for some reason. But the bromine can approach from the top or the bottom face with equal probability because it's sp2 hybridized. I just have a tendency to look at it from the top for some weird reason. But it doesn't matter. And so what's going to happen? Same mechanism. We're going to have this attack, this break, and then the lone pairs on this bromine come in and attack. Okay? So we're going to have, let's just, we're going to now have that Br plus, like that. And based off the answer, we saw that water, where did it attack? It attacked the more substituted carbon, broke that bond like so, and gave us this right here. Now, do you see how I'm leaving this bond right there? I'm leaving it up. And then these wedges and dashes, I just leave them as they are drawn. Just leave them. And then what? The water came in from underneath, like that. Like this. That would have to be positively charged. We do a proton transfer mechanism, and we get rid of one of those hydrogens to give us our product. Just like that. So why does the water prefer to attack this carbon and not that one? And the reason why is the simple, quick answer is the fact that this carbon has a much larger partial positive, well, a much larger positive, partial positive than this carbon. So let's draw it a little tiny. That has a larger partial positive, so the nucleophile is going to be attracted to the stronger electrophile. Okay? Now, why is this one going to be the more positively charged species? It comes to the fact that, hey, when we look at the bromonium here, these bromonium bonds this bond right here is very, very weak. Let's do it let's do it the other one. That would have to be positive. Okay. So you can see how I've dotted. Why is this bond more partially broken than this one? That's because if this bond is partially broken, it's going to have what? A partial positive, right? But what can stabilize that partial positive? The alkyl groups are electron donating, so it helps to stabilize that partial positive. In comparison, the partial positive over here doesn't have alkyl groups to help stabilize it. All it has is hydrogen atoms, and hydrogen atoms aren't electron donating to help stabilize it. So the bond that's going to preferentially break is going to be this one, because it's going to give us a stabilized partial positive. So the moral of the story is when you have a unsymmetrical alkene, the water is going to attack the more substituted carbon because of these reasons that I've just explained. So you could envision a test question to make sure you understand this principle, because I could give you on a multiple choice test, okay, we could give you like 3 to 4 different structures just to make sure you understand the regiochemistry of this reaction. So we could say something like this. So we could say molecule A, molecule B. We would have molecule C's and D's. But I could make the question in the way that, hey, what is the major product here? Or what is the product of this reaction? And you have A and B. Or the answer choice could be a mixture of A and B. Can we have a mixture of A and B? No, we can't. It doesn't happen. So our only answer would be B. We also have to make sure that the stereochemistry is correct. What's the stereochemistry? It has to be anti. Okay. So let's, I'm going to do one example to show this. Okay, so I'm going to pause the video and do one more example. Okay, so here's a test question that you could potentially see that tests to see if you know all the ins and outs of halohydrin reactions. Okay, so here's the starting material, here's the reaction, here are the 4 answer choices. I would pause the video and don't even look at these answers. That's a big test tip. When you see a reaction here, don't look at the answer choices. Look at it, solve it. Use the mechanism, solve the reaction. Once you have an answer down on your paper, then look at the answer choices. So I would pause the video, see what you get. What's the correct answer? Now, when we come back, we'll talk about it. Okay? So let's talk about it. Which is the correct answer? Okay? Well, let's just go through the incorrect ones. This one right here, why is this answer incorrect? Well, the regiochemistry is correct because the water attacked the more substituted carbon. That is correct. And so that means the chlorine would have to go to the other carbon. That is correct. But look at the stereochemistry. They did what? That is syn addition because they're both wedges. That does not happen because we formed the chloronium ion. And so the attack has to be from underneath or on the opposite side. So what's wrong with this guy? We have syn addition because we see they're both wedges, and the regiochemistry is wrong. The alcohol doesn't go on that carbon. So that thing has two things wrong with it. Now if we come to this one right here, oh, we see that they are what? Anti to one another. That's a good thing because that's a wedge, that's a dash. But the regiochemistry is wrong. The alcohol is supposed to go where the chlorine is. And then we see that by process of elimination, that would have to be our correct answer, right? But we see that the alcohol goes to the more substituted carbon, and the chlorine goes to the other carbon. And what's the stereochemistry? They are anti from one another. So that is exactly what we want to see. Does that make sense? Those are kind of the test questions you're going to be given to make sure you understand all the ramifications of the reaction. The next addition reaction that we're going to look at is when we take an alkene and we treat it with a reagent that I'm not going to show you quite yet, but we get addition of two alcohol groups. That is called dihydroxylation. Now, look at the stereochemistry here. Is that syn addition or anti-addition? You can see that we have a wedge and a dash. So what we have is anti-dihydroxylation. We also have reactions where we can add these two OHs syn to one another, both wedges or both dashes. We will look at that reaction momentarily, but for right now, we are going to take a look at anti-dihydroxylation. And the reagent that's used to make this transformation right here is a two-step process. Is where you treat it with CO3H, and that compound right there is called a peroxy acid. And I'll talk a little bit more about that in a moment. And then step two, we add some aqueous acid there. And that's going to get us this transformation. So the peroxy acid, okay. Well, before I talk about peroxy acid, what is this functional group? That guy right there, what's that called? That is what? A carboxylic acid? Yeah, that is a carboxylic acid. A peroxy acid is one where you just add in an oxygen there, then the hydrogen. So that right there is a peroxy acid. And you can see that this chemical formula right there matches that right there. So that is a generic peroxy acid, but one that we use in organic chemistry all the time is called MCPBA. Make sure I got that right. And so what does MCPBA? So what we could do is basically say, hey, get rid of that and go MCPBA. What does that stand for? That stands for meta chloro peroxy benzoic acid. Metachloroperoxybenzoic acid. So that has a structure that looks like this. Well, we know we have a benzene ring. Benzoic acid looks like this. That's benzoic acid, but it says it's a peroxybenzoic acid. So we would just stick in our other oxygen there, like so. And then there's this meta business. So that's meta right there, right? Now what's on the meta position? A chlorine. Just like that. So let's see, what else do we have? So that's the ortho position, meta position, para position. So metachloro. Perfect. So that's a very common peroxy acid that you use to make this transformation occur. Now what's interesting is if we break this down a little bit, is after step 1, okay, after step 1, we can have the MCPBA. What it's going to do is it's going to convert the alkene into a peroxide. Not a peroxide. 3-membered ring with an oxygen. Epoxide. There you go. It makes an epoxide. And then after you make the epoxide, you do step 2, which is adding the aqueous acid, and then that will turn it into our our product like that. So it goes in stepwise. So now let's look at the mechanism of how MCPBA turns the alkene into an epoxide, and then how does the epoxide, when treated with some acid, turn into the product there, or the dihydroxylation product. Okay? So let's take a look at the first reaction where we're treating the alkene with the peroxy acid. I want you to understand that this molecule is in the plane, but if we flip it, we're going to make the, what I've been doing this whole time, right? Where it looks more like that. So the peroxy acid, so this molecule's in the plane, this one in pink is rotated by 90 degrees. So the peroxy acid can approach from the top face of the molecule or from underneath. It's a 50-50 chance. But in order to draw this mechanism, it's a little bit more difficult to do it when it's in this orientation. It's easier to do it when it's in this orientation. But you need to understand that it is happening on one face of the molecule. You could look at it in this perspective, top face, bottom face. Or you could look at it in this perspective and say front face, or go behind and come back, the back face. We're saying the same thing. It's just how the molecule's oriented. So what I want to do is look at it this way, okay? But you have to understand that this peroxy acid is approaching. Okay, so there's that. No. Let's see here. You know, it's going to be easier for me to draw it a little bit differently. So let's look at it like this. Okay. So we're going to have ROHO. R. Okay, so when you do this mechanism, what I like to do is I find the alkene, okay, and I didn't do it the best here, so let's actually show you what I would want you to do. The way to do this mechanism is I find this carbon and I just go out a little bit and draw my first oxygen. This carbon, go out, draw an oxygen. And then we have, and I'm going to put the hydrogen cocked this way, and you'll see why I want to angle it that way, because I'm going to then draw the carbonyl oxygen like that, and there's my R group. So I hope that you're seeing, the reason why I'm doing this, because look at this. We're going to have, oh, how do I want to say this? Well, you'll see in a minute when we draw the arrows why this, you have to, it's best to draw it like this, okay? You could have very well have drawn it like this. Well, you could have very well drawn it like that, but that's not going to prove useful in the mechanism. So you need to draw it like how I showed you here. Like so, okay? So the first thing that we need to understand here is there's going to be 5 arrows here to keep track of. All right, 5 arrows. So the first arrow here, I just don't want to make, since there's 5 arrows, let's get this right here. So this pi bond right here is going to come in and attack that oxygen like so. Okay. And then this oxygen-oxygen bond is going to break like so. And then this carbonyl right here is going to take the electrons like so to grab that hydrogen. And then these electrons in this bond right here are going to come in and attack the carbon. So what's that going to give us here? That's going to go like this. We have now formed a epoxide. You see how this pi bond here forms a bond right there? And then the electrons right here come in to form the bond with the carbon as well. So here's our epoxide. Okay. And then what do we have left over? We have this oxygen. This oxygen is this guy, double bonded to a carbon, which has an R group, which then this grabbed put the hydrogen on the oxygen. Look at that. So what did we generate? We generated a epoxide and a carboxylic acid. So put that in your notebooks. How to make functional groups. How do I make epoxides? Well, this with the MCPBA. MCPBA. And then how do you make carboxylic acids? Well, you could treat a peroxy acid with an alkene to give us a carboxylic acid. All right? Okay, now we have our epoxide. So do you see how I have wedges here? Because I'm representing that the peroxide approached this molecule from the front face. It very well could have approached it from the back face and given us an epoxide with dashes. That is very possible or plausible as well. It just, how does the peroxy acid approach? Front face or back face, okay? So now that we formed the peroxide, let's take a look at what happens next. So in the next step, after the epoxide's formed, you treat it with our acid, right? And so what's going to happen first is a proton transfer. So what does that look like? If we extend out the hydronium to look like this, this is going to come in and protonate the epoxide. Okay. So that's going to, no, there we go. That's going to protonate the epoxide. And what happens when that protonates the oxygen, it weakens one of these bonds right here, oxygen-carbon bonds. It gets very, very weak. And so we've generated some water after this step. And now the water is going to attack anti. It's going to come in like so. And now we're going to get our product. I'm going to draw it down here. This bond just stayed, so that's just straight up. Oh, and it already has a hydrogen there. Perfect. And then water came in from underneath, like so, but that has to be positively charged. And so now we do another proton transfer where we take some water and do the proton transfer step to give us our final product. And I can draw it, like this if we'd like. You can see that they are anti, and we would then also say, hey, we have the enantiomer that we would have to account for as well. Okay, isn't that cool? So that's how you do it. Now let's take a look at syn dihydroxylation. Syn dihydroxylation. So here's a syn dihydroxylation. Now, one thing that we need to remember that I may have said, but I can't recall if I've done that. Whenever you have two alcohols on adjacent carbons like this, we call that a diol. So you can have syn diols or anti-diols. The stereochemistry doesn't matter, but just when you have these two alcohols next to each other like this, we call that a diol. So in a syn dihydroxylation reaction, you can see that both hydroxyl groups are wedges. They could have been both dashes as well, as long as they're just on the same side. Now, in order to do this transformation, there's going to be 5 chemical reactions to be aware of. I have 4 written down right now. I'll show you the 5th one in a moment. But the key player is osmium tetraoxide. Okay? Osmium tetraoxide treated with sodium sulfite, and some water will bring about this process. But please note that it's a 2-step process. You do the reaction with the alkene with the osmium tetraoxide. You will isolate a product, which I'll show you in a moment. And then you take that product and treat it with the sodium sulfite, and it will convert it into the diol. In this one in blue, we see the osmium tetraoxide, but now our base is just slightly different here. Now it's what? Sodium hydrogen sulfite. Okay. So those are very similar. It's just that second step is just slightly different. Now, osmium tetraoxide is very, very expensive. So they're trying to figure out ways to do this cheaper and to use only catalytic amounts of osmium tetraoxide. So here we're going to put cat for catalyst. So we have small amounts of osmium tetraoxide for both of these processes, but what's different is what we're adding to it. Now we're adding a whole lot more of this NMO, which is represented by this molecule, and NMO stands for N-methyl morpholine N oxide. And when you do these reagents, you get the same product. It's just now we're using less of the expensive osmium tetraoxide. And another thing you could do, shown in orange here, we could use this tert-butyl hydroperoxide right here, okay, to do the same transformation. So those are 4 reactions, conditions to generate our syn diol. Now the 5th one is where you can take potassium permanganate. Okay. And this is done in one step. Let's see here. Let me double check one thing. Okay. So yes, it's potassium permanganate with some sodium hydroxide, but this is key. It needs to be cold. Cold, cold, cold. And the reason why is potassium permanganate can oxidize other parts of your molecule when it's warmer. So you're controlling this reagent to just do one thing. That's the hope when you do it at a cold temperature. Okay. Now, we need to understand not the whole mechanism of all these transformations. You just need to understand the first part of the mechanism so that you can understand why we have syn addition and not anti-addition. So that's what we're going to look at next. So the reason why we get syn dihydroxylation to occur is because the way osmium tetraoxide reacts. It reacts in a concerted fashion. And so osmium is going to approach the alkene from one face and do all its reactions in a concerted manner. So what we can see here is something like this. Right? And so when we do that, do you see here, we added the lone pair there, and we added these 2 oxygens right here. So this oxygen and this oxygen are coming from these 2. Do you see how they've just attached on the same face in a concerted fashion? And then you make this osmate ester, and then you treat it with step 2 of your conditions, and that will then chop this off and convert them into an alcohol. So you don't need to know how this gets converted into the diol. Okay, those mechanisms we don't need to worry about. You just need to understand this first part because it explains why you get syn addition, because it is a concerted process. Okay, so I think that looking at the time on the video, I think that's where we will conclude. Okay, reach out. Please reach out if you have any questions or concerns.